Well, hello there. Welcome to my channel. Welcome in a long time. So I was busy in my studies, so I couldn't make uh, much videos on circuit analysis and EMF, which I am currently focusing on. So without ado, let's get started with this video. So today I'm gonna talk about circuit response, which is also a part of systems analysis. So in my previous circuit analysis video, I derived the equations for the source free response of a second order system, a second order electrical system, which is the series and parallel RLC circuit. I derived the equation in both time domain and frequency domain, and then I solved the equation. So today I'm gonna um, explain you, or I'm gonna discuss about the system behavior, the behavior of a second order system, in this case an electrical system, and what the behavior looks like. Okay, and how are the terms how are the terms psi or zeta, however you may write, or zeta and omega n, uh, and as a matter of fact, which is omega d. So these two terms define, or these two terms determine a system's behavior. It doesn't have to be an electrical system, it can be any kind of dynamic systems. And our real world systems, the systems we observed practically, are all dynamic systems. Whether it's an electrical system, electric systems are mostly circuits, and mechanical systems, chemical systems, biological systems, you name it, all kind of dynamic systems. There are no perfect static systems, I remind you. So so all kind of dynamic systems, uh, beyond first order, beyond first, from second to higher order, have uh, single to multiple damping factors, uh, damped natural frequency, or internal frequency. Every system has it. Okay, so let me first discuss about these two terms in general. Okay, so in systems theory, damping, the term damping refers to, in general, universally, so the decaying of energy oscillations in a system. So damping can be either internal. So internal damping is mainly damping. Let me. So internal damping occurs. Internal damping is kind of damping that always exists in a system. It it exists in a system by nature. Okay, so the internal damping is caused by systems. Internal damping always exists in a system, no matter what. It's nature, it's by nature. Okay, it's by default. A system possesses internal damping, some kind of damping, by its nature. So internal damping can arise due to system's internal frequency, internal friction, it's the system's material properties. Basically, the dissipation mechanism of a system causes internal damping. And the second type of damping is the external damping. External damping is a kind of damping that is introduced externally to control the system's behavior. So external damping is introduced to a system from outside to control the system's behavior. Okay, so these are the two basic dampings. So in electrical systems or mechanical or in systems in general, so damping is measured by a parameter called damping coefficient or damping factor, which is denoted or expressed by zeta or psi, and or it is expressed by Greek letter sigma. So throughout this video, for um, explaining purposes, I'm gonna use another term, which is Nepper frequency. Okay, so Nepper frequency is also a term that is related to the damping coefficient, damping which is also called damping factor. So Nepper frequency. So Nepper frequency is the frequency rate or the rate of decaying. Okay, so the frequency at which the energy of a system dissipates. So rate of energy dissipation. So rate of energy dissipation, I'm gonna denote this by sigma. So sigma is related to the damping coefficient, and damping coefficient is denoted by damping coefficient is denoted by psi or zeta or whatever. It is also called damping ratio. So this is the basic idea of damping. I am using the electrical systems as basis. Damping in general exists in all kind of real world physical systems. There's no system that's real, that's physical, exists in nature that doesn't have damping. Okay, so the undamped systems only exist in theory. Okay, so undamped systems have uh, energy oscillation that doesn't decay. So now what I'm gonna discuss about is the internal natural frequency of a system. A system can be either electrical or mechanical or chemical or any kind of real um, dynamic system can have one or multiple natural frequencies. Okay, it is uh, it is a must for any physical natural dynamic system. A system always has one or multiple natural frequencies. So what is this internal natural frequency of a system? So the internal natural frequency or frequencies of a system is the rate at which a system, a dynamic system, if I may add, a dynamic system, and remind you that the nature is by default dynamic. Okay, everything in nature is dynamic. So so the rate of the rate at which a dynamic system naturally oscillates or resonates after 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 being disturbed by external forces from its equilibrium state. So this natural frequency, when we consider ideal case, the undamped case, so uh, when say we are not including the damping factor in the system, this natural frequency is the undamped natural frequency, and which is described by 1 by root LC. This equation is mainly for the RLC circuit, the electrical system. This RLC circuit is a second order system, and for mechanical system, the equation will change obviously. So this is the natural frequency. And it's an interesting fact that every dynamic system that can store or exchange energy has natural modes of oscillation. So this mode of oscillation is the natural frequency or frequencies. Higher order, this is at least a system has to be at least second order to have one frequency, at least one natural frequency. Um, higher order systems have multiple natural frequencies. So this internal natural frequency and damping factor are key to understanding the behavior of a dynamic system. Understanding these two parameters especially will help in uh, signal processing uh, and communication and power system stability control. If I am focusing on electrical systems and any other dynamic system engineering. Okay, so these two parameters are so important because basically engineering fields are uh, every engineering field consists of signals and systems. So a little earlier I had introduced a term called Napier frequency, which is closely related to the damping ratio or damping factor, damping coefficient of a system. So I'm gonna uh, establish a new relation among the terms I have introduced you so far. So I'm gonna denote damping factor as a ratio of two frequencies. So I'm going to define damping coefficient or damping factor as ratio of two terms, which are the Napier frequency divided by the undamped natural frequency. So what it will do is that I'm gonna define the damped natural frequency, which is omega d, by this equation, which is omega n square minus zeta or psi square. So now what I'm gonna do is, as psi is this, so this coefficient will become Napier frequency. So this is also this the Napier frequency. So so damped natural frequency is the combination of undamped natural frequency and Napier frequency. Okay, so this becomes omega n square minus omega n square psi or zeta square root over. So which becomes 1 minus psi square. So in throughout this and next video, my next system response system analysis videos, I'm gonna use this definition. Okay, so omega d is basically what it is. So this is Napier frequency and this is natural frequency, and this is omega d. Okay, so this is omega d, and the damping ratio or damping coefficient is the ratio of Napier frequency and the undamped natural frequency. In my previous circuit analysis videos, I have derived the circuit response equations, the loop current and node voltage of the series RLC circuit and the parallel RLC circuit respectively in both time domain and frequency domain. Okay, so in this video I'm gonna express those current and voltage responses in terms of in amplitude phase form. Okay, so to do that, I'm going to define the Napier frequency, damping ratio, and everything else, NU. So Napier frequency. So for this two, so for the series RLC circuit, the Napier frequency will be, so I am denoting the series, the Napier frequency for the series RLC circuit as sigma s, which is R by 2L, and the parallel circuit Napier frequency for the parallel RLC circuit is as sigma p, which is 1 by 2RC, if you remember this correctly, and damping coefficient or damping factor, which is zeta or psi. I am writing psi, so which is the, I have earlier, as earlier I have defined psi as ratio of Napier frequency and undamped frequency. So for both cases, for both series RLC circuit and parallel RLC circuit, omega n is the same. So under natural frequency is omega n is 1 by root LC. So omega n, so for series RLC circuit, the damping factor is, so if I take the values, it will be R by 2L by 1 by root LC, which is R by 2 root over C by L. And say the damping coefficient or damping factor for the parallel RLC circuit is psi p or zeta p, which is sigma p by omega n, which is 1 by 2 RC by 1 by root LC, which is basically 1 by 2 RC root over L by C. So these are the things I have defined here. So what I'm going to do now is I'm going to express the current response and the voltage response in amplitude phase form. So in my previous circuit analysis video, when solving the current response of the series RLC circuit, I found current response to be the full response, which was IT, the loop current, which is equal to exponential minus, so here damping the damping term will be replaced by the Napier frequency, the frequency at which the energy oscillate the energy decays in the RLC circuit. Now, so in my previous expression it was psi or zeta t. Okay, so I'm replacing this by sigma, which is the Napier frequency, as I have uh, newly defined all the terms. So IO so this is the current response for the series RLC circuit. Okay, so now what I'm gonna do is I'm gonna express this in amplitude phase form. So if I say that I O is the Im cos delta I, and the term Vo by omega dl minus sigma by omega d io is Im sine delta I, where Im is root over I square plus Vo by omega dl minus sigma by omega d io squared, and this is the phase difference, phase shift. So phase of this response is tan inverse Vo by omega dl minus d io by io. So if I define that all the terms like this, it will give me current response will become e to the power minus sigma st, because this is the response of the series RLC circuit. The amplitude and write this clearly. So cos omega dt cross cos delta I. So this is the amplitude phase form for the current response of the series RLC circuit. Now I'm gonna express the voltage response of the parallel RLC circuit in amplitude phase form. Okay, so in my uh, previous video of the circuit analysis for the parallel RLC circuit, I found voltage response. So let me write it here. So the full voltage response of the parallel RLC circuit is e to the power minus sigma t Vo cos omega dt minus Io by omega dc plus sigma by omega d Vo sine omega dt. Now so here also I wanna express this in terms in amplitude phase form. So let me assume that Vo is Vm cos delta V. So Vm is the amplitude and delta V is the phase, and IO by omega dc plus so this term I'm defining it as Vm sine delta V, amplitude and phase. Now Vm will become Vo squared plus Io by omega dc plus sigma by omega d Vo whole squared, and the phase will be, this is the amplitude, and the phase will be tan inverse Io by omega dc plus sigma by omega d Vo by Vo. So this is the whole case. Now the voltage response of the parallel RLC circuit in amplitude phase form will be Vt exponential minus sigma p for the parallel RLC circuit, and Vm now it will be, so this is the amplitude phase form, obviously the decaying amplitude phase form for the parallel for the voltage response of the parallel RLC circuit. So now I'm gonna tabulate, I'm gonna prepare a comparison table of the circuit behavior, or the system behavior of the electrical system behavior for different damping conditions. So here you can see that I have made a comparison table. The leftmost side the leftmost side column is for the damping conditions, where I'm gonna set the values of damping ratio and the relation between the Napier frequency and the internal undamped natural frequency. And I'm gonna see in this column here, this column is about the root location of the complex frequency plane, and I'm gonna see the response of the system. And uh, after seeing the response of the system in the rightmost column, I'm gonna write down the system conditions. Okay, so our first damping condition is, so I'm gonna start with when the damping ratio or damping factor is 0. So when this is the case, the Napier frequency is also 0, for which the characteristic roots, so the roots are minus sigma plus minus j omega d. Okay, so as Napier frequency is 0, so the roots are omega, sorry, plus minus j omega d equals plus minus j omega n, because omega d is, so this is the root, the equation for the roots, so on S plane. So when the damping factor or damping ratio is 0, Napier frequency is also 0. So for this damping condition, the roots will be plus minus j omega n. So the root location on the S plane is, so this is j omega, and this is Napier frequency, the real axis and imaginary axis. So the roots are on the imaginary axis, exactly on the imaginary axis. So this is plus j omega n, and this is minus j omega n. So because the roots are literally on the imaginary axis, the response will be undamped, and the equation will be for the current response. So the current response will be Im cos omega nt minus delta I. The response is basically in time domain is, it is this, there's no damping, so this is current response it, and the voltage response is basically Vm cos omega nt plus del V. This is also undamped, so in the time domain it is perfect oscillation. Okay, so this kind of system condition is undamped condition. There's no damping, the exponential term has vanished. Okay, and omega d, the damped natural frequency, has become omega n, the undamped frequency. So this is the undamped case for system. So I am describing the system behavior for using the electrical system, using electrical systems. Okay, so this is the case for any kind of system, mechanical and etc, etc. So this is the undamped case. So system condition when damping ratio is 0 is the undamped condition. Now number 2 is when damping ratio is greater than 0 but smaller than 1. What will happen then? Then the Napier frequency exists, but it is less than the natural frequency, for which the roots will be basically minus sigma plus minus j omega d. Everything exists, and the root location, let me see where it is. So the real axis is the Napier frequency axis, and the imaginary axis is j omega, the natural frequency axis. So the roots are on the left half side of the S plane. So these are the roots for this condition. So the circuit response is basically the power, the damping exists in this case, but it is less than the natural frequency. So the damping factor won't be able to decay the energy sufficiently. There will always be a certain oscillations around the equilibrium position. So for the source free RLC circuit, or the source free electrical system, so the equilibrium position is the t-axis or this axis that goes through the origin. Okay, so e to the power minus, so here for the series RLC circuit it is st im cos omega d minus delta I. So the response is basically this in time domain. Okay, this is time domain, mind you, and this is it. And the voltage response is e to the power minus sigma pt for the parallel RLC circuit, Vm cos omega d t plus del v, and it looks like basically the same with phase shift. So this is basically this. Okay, almost the same. So there will be some phase shift here and there. So this is the basic response. Okay, so this is the case where the system is underdamped. There is damping uh, present, but there is also oscillation present in the system. Okay, so this is underdamped. This is underdamped condition. Now for the third case, if damping ratio becomes equal to 1, what will happen? The Napier frequency will be equal to the natural frequency of the system, for this case RLC circuit. So for this, the roots are equal and on the left half side. So say the characteristic roots are minus sigma. So the roots are basically here. The two roots are here. So this is sigma, this is j omega. So the roots are basically here, and so I have forgot to tell you that I am considering positive damping. Okay, there's also negative damping. So this is positive damping, and because the roots are the same, the circuit response won't be the equation for the circuit response won't be the same. So I have done my I have derived the equation for the critical for the conditions. So when roots are the same, the differential equation solution becomes different. The method of solving the differential equation becomes a little bit different. So I have derived it. So it is the basically the equation is IO minus sigma IO plus VO by L T e to the power minus sigma st sigma s. So this is the equation. So this is the equation uh, so this is the equation when roots of the characteristic equation for the RC circuit are the same. So for this, the response will be, so this is the case where the Napier frequency is equal to the oscillating frequency. So the response will look like this for the current in time domain, and voltage response is, the equation for the voltage response is VO plus sigma P VO minus IO so this is the equation. Okay, so this is sigma P. Okay, so the response is basically, it basically looks like this. Okay, it crosses, sometime it crosses the x-axis, the real axis, or sometimes it doesn't. So there is no oscillation here. The system quickly returns to its equilibrium point, which is the time domain, which is this axis in time domain. So this type of system condition is critical damped, where the Napier frequency is just equal to uh, to balance out the oscillating frequency. So this is critical damping. So this is critical damping, and 4 is when when the damping coefficient or damping factor, damping ratio is greater than 1. What happens then is the Napier frequency is greater than the oscillating frequency. So this is basically, the roots are now sigma plus minus omega d. There is no imaginary term. So in the complex s plane, so j omega, so the roots are like this, not the same. So the equation is basically c1 e to the power lambda 1 t plus c2 to the power lambda 2 t. I didn't do the extra derivation here for this. So this is current response and this is voltage response. They're basically the same. The roots are just the roots are real. Okay, pure imaginary root. So c2 to the power lambda 2t. So this response is delayed response with no oscillation. Okay, so the response is delayed response. So this kind of damping condition is overdamped, where the Napier frequency, the damping frequency is just it is greater than the oscillating frequency. So these are all the damping conditions for a system, a second order system. So these are all positive damping. There is also negative damping. When negative damping occurs, it it that kind of negative damping, what is causes is, it basically grows the energy of the system. It instead in undamped condition it's the same. Undamped condition, when underdamped, instead of decaying the oscillation, it it helps in increasing the oscillation of the system. So instead of decaying, it becomes increasing. So these are the basic two damping condition, positive and negative. I am showing you the positive damping condition because Positive damping conditions are the most practical and efficient and you studied in control systems and system behavior, in system theory in general. And sometimes in theory, uh, negative dampings are discussed also. It's not totally uncommon. So these are the system behavior, especially for the source free RLC circuit. So I hope you understood my explanation, and thank you for watching this far. And uh, I will be happy if you subscribe to my channel. So that's it. Thank you for uh, watching.